This will this this will be a quick talk. Hello again. This is a talk on collapsed forwarding, basically inspired from Leif's talk before. So Roger touched briefly about thundering herd and the problem that can cause in CDNs and origins when that happens. Thundering herd essentially is a situation where you get overloaded with a resource, a request for a resource with multiple clients at the same time, exactly at the same time, and you're not able to serve that many clients because you're simply overloaded, basically. So that's a common classic problem that can happen during live streaming or other use cases where you have a situation where multiple clients are requesting the same object from the cache exactly at the same time. So today we'll talk about what ATS offers to address that, and what are the limitations in that, and what is the proposal to fix that, basically. So this is the basic ATS state machine. I just copied it from the doc site. Maybe it's not entirely latest, but it gives a general idea. Just the request states, how we jump from each state through the cache states, and then finally the response. This is assuming a cacheable content thing. So looking deeper into the cache state machine, this is how it looks. When a request arrives, and once we reach the cache state, like after we finish the read request and what are the states that were there before, ATS does a lookup for the object using the request URL. That's the default cache key. If you have it overridden with a plugin, then that's the cache key that it uses. If the lookup is successful, the next thing it tries to do is try to get a read lock on it to read and serve. If the read lock is available, it serves, no problem. It's a simple case. If it's not if the lookup was not successful, that's a cache miss. Then the next step, next state that ATS cache jumps to is open cache write. It basically tries to get the write lock to be able to download from the origin, fill the cache, as well as serve in parallel. So yeah, open cache read. If it's success, serve from cache, else go to write. It's pretty simple, right? If open cache write, it's able to get the write lock. The dirend is locked. Object is downloaded from, streamed from the origin, and also streamed to the client to the cache, and then things move on as usual. If the write lock is not successful, typically that can happen if there is a parallel request that already acquired the write lock for the same object, or for the same cache key. So then the default behavior of ATS is to simply turn off cache for that particular request and just tunnel the request as a proxy-only scenario. This is generally okay when there aren't many requests that hit this scenario, but in a live streaming scenario, you can imagine that you can have millions of clients asking for the exact same object, same segment in the case of video, at exactly the same time. And if the CDN, if the delivery server sees cache miss for all of them, only one of them is able to get the write lock, and rest of them just end up going to the origin. You can imagine it fills up the pipe pretty fast. I mean, these are video files we're talking about, and they're usually pretty large, like megs. Depending on the bit rates, you have multiple of them, and then imagine this happens on each server separately. So we have had quite a few outages because of that in the past. So thankfully, ATS offers some built-in solutions already to this. Number one, it's read while writer. I think Roger touched upon it as well. Basically, the way read while writer works is if the object is being returned to by the writer, by the thread that acquired by the transaction that acquired the write lock, it's already in a state where another transaction can hook and start streaming from it, which is typically after the response headers are arrived, because that's when ATS knows that this is a cacheable response or not, and then start allowing other transactions to stream off of it. It is able to do that without issue. So that's the read while writer feature. It has some other related settings. You need the background fill threshold, background fill timeout, etc., which are to ensure that you have a minimum amount of data to start streaming before you get there. But the docs say, and we also did this, is to disable those, because For a use case where it's heavily cache dependent, you don't care whether you reached certain threshold or not. You want to stream as quickly as possible. But like I just described, there is still that window until the response headers are arrived where the object isn't there in the cache, nor the reader can start streaming from there. So that's the window where live streaming or other concurrent request scenario can cause a thundering herd problem. And I mean, it's actually a tiny window if you look at it, but depending on the use case, it could result into a big problem. So there are other mitigations to work around that. Number one is open read retry. So typically what this does is if the open read fails, it keeps retrying with a delay in a loop. Basically, there's a couple of settings, number of retries and delay between each retry. This can be enabled independent of read while write, but it is generally recommended to configure together because you want to start streaming while the writer is happening. Otherwise, you would have to wait until the entire object is downloaded to start streaming. So it's not that great if you don't have read while write enabled. Then there is open write retry. This is actually not that useful. I don't know if anyone uses this. So what this does is, again, similar to read retry, it tries to retry for the write lock. But at least looking at the code, and I think we've tried it in the past as well, what it does is if eventually the write retry is successful, it again tries to download the object and writes to the cache, which is really not that useful to you. I mean, I don't know why anyone would want this setting. So the other setting that we added to work around is open write fail action. So this is like if you failed, you exhausted your open read retry, and you still could not get the read lock, then you jump to the, if you go back to the previous slide, you jump to the cache open write. And this action basically says that if you failed the write lock at that point, because the other transaction is holding the write lock, what do you want to do? Whether you want to just tunnel to the origin as a proxy only, that's the default behavior, or you want to do some other mitigation. So what we did was to return a 502 error from the core along with a et header. So that's one use case of et header. We added an et header to be able to let a plugin or other custom mechanism to use that et header to do internal retry or whatever. So yeah, so the other requirement or the other thought around this write fail action was to serve a stale copy if it was a cache refresh scenario. For cache miss, it would return a 502, and for cache refresh, it would return a stale copy. Yeah.
If you go back to that, like the open read retry, like one of the things I couldn't find is there a statistic to tell us how many times we have done the retry or something like that? So without that, it's hard to know like how effective this is, and how do I set how many retry is reasonable or suitable for my particular application.
Yeah.
So this is like some of the things that puzzle me when I think how many times I should retry, and there's also the timeout as well too. Like so.
Right. Yeah.
Yeah. So that's. So, I think this is an art to know how many times you have to retry.
Right. Yeah. That's a good point. I think we can instrument to add something there, but I believe there's some milestone around it. I don't remember. This was a long time that I looked at it. I don't know if it actually captures the number of retries, but you actually could see the delay it took. And you could basically see how many retries happened. Because
so that's not very scientific.
That's not very intuitive.
It's just infer that maybe
that's true.
It is 3 times versus 4 times.
Yeah, totally. Yeah, I think we can. When I add the, when I implement this, we can definitely instrument that too. Yeah. Okay. I see. Okay. Yeah, it'd be good to have it built into the core and rather than having to write a system tab thing, but yeah, that's good. Okay, yeah. Where were we? Yeah, so that's the open write fail action. I think I got the slides backward. Yeah, so building on that, we wrote a plugin called collapsed forwarding. Essentially, what this plugin was doing was to intercept, not intercept in the ATS terminology. It's more like grab the 502 signal on send response hook, I think. Instead of sending back the response to the client, it would basically look for this other header, which said that this happened because of open write fail. It would actually initiate a redirect request with a delay. The redirect request is essentially to make the request go back through all the states, in particular the cache open again, because from a plugin there was no way to jump states back. So that was the solution that we implemented, like a few years ago. So that and that redirect follow was also configurable. How many times you would want to retry, and how many redirect, and how much is the delay between attempts. And at the end of it, what you want to do, like if you still could not stream, or still the object wasn't downloaded, what you want to do is also configurable, I believe. So this plugin worked well for us for our video use case. For all the cache misses, we were able to collapse the requests very efficiently. I think we actually managed to get to a single request from a single server to that level. So it was great, but it didn't quite work for cache tail. We didn't spend a lot of time on why it didn't work. It was working sometimes and not working sometimes. There must be some bug in it, but it wasn't a concern for us because usually refresh was for the manifest file, which is really short. So we didn't really look into too much. But as you can see, this was a band-aid solution to what could have been solved in the core. And it also is inefficient because it requires looping a new request, so more resources, more memory, and more processing. So then Leif yelled at me saying, why do we need this open write fail action? Why don't we do something different to solve this problem within the core rather than relying on plugins and stuff? So we had a discussion offline, and yeah, he convinced me to go back and look at the code. So looking at the HTTP cache SM, so the behavior is that when open read retry, the way open read retry works is that if the cache SM returned a doc busy, only then it would actually do open read retry, which makes sense because you don't want to delay your open read for a simple cache miss scenario. Like if it's a first cache miss and there is no real concurrent requests on that, you don't want to delay. So there was nothing we could do on the open read state itself. But then the open write is where we could, is where I think we are looking to improve. Today, what happens if open write fails is that the retry eventually gets you back to write action, meaning it will try to write to the object. But what we really need is to move that back to open read when the write fail happens. And if we did that, yeah, so when open write fails, that clearly indicates that it's because of a concurrent request. There was someone else holding the write lock. And while you are retrying, if the retry, yeah, at that point you jump back to open read after certain delay, then you can get back through the read while writer again. The advantages are that this will be built into the core without having a need for new plugins or not worrying about other things. You just have one setting that you need to configure. And it's a lot more efficient because it's just scheduling continuations internally in the core as opposed to triggering a new request, and it's like a lot confusing. I think this will also address the cache stale scenario because for cache stale, the code path, I believe, is different, which is why the previous fix wasn't working. Because for cache stale, your open read actually is successful. It is successful, and then you jump to whether you can serve from there, and from there you go to open write as opposed to the normal open read fail, open write fail sequence. But this should fix the cache refresh as well, because once you have the cache write fail and you jump back to cache open read at that point, that means you're able to stream even a stale copy. I mean the refresh scenario. Wins will be we can deprecate the plugin after this solution is implemented. And I think it indirectly results in stale while revalidate. It's not exactly as the RFC says, because you're not actually serving stale copy. You will actually end up serving fresh copy to everybody with a small delay. I think it's equivalent of stale while revalidated, or maybe better even. We already deprecated the stale while revalidated plugin for other reasons too, so I think this is reasonable. So, Ivan, you had questions on this? Does this look okay, or like, what are your thoughts? Okay, 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 cool, yeah. Okay. Okay, cool. Yeah, then we can, yeah, if you already have that, then we can just sync up and get that.
So if these requests are getting into a loop, where do they exit? Right? Where do you overflow when you have too many clients waiting for the server response? Or do you start shedding in new requests so that you don't overflow memory or something?
I'm sorry, I didn't get it. These requests are just scheduling continuations to come back and check in. Just schedules an event into the future.
Right, but
yeah.
Those accumulate
Right.
to a point of critical failure. How do you start shedding them?
Oh, so with the plugin, we had this fallback scenario where you exhausted all your loops, all your checking back stuff. So we configured it to return an error back to the client, and our clients, the video player, also had a built-in resilience to retry when that happens. Yeah, I guess we could do the same thing even with that. So we would have a fallback action, whether to tunnel at that point or return an error.
But is there like a number of times that you retry, or
yes, yeah,
a
it will
limit
still be
on
controlled
how many?
by, yeah, it will still be controlled by these settings: open, read, retry, number of times, and the delay you want between them. And in most cases, we actually saw that the values we were using were, I believe, 50 milliseconds and like 5 retries or something, and our P99 was 1 retry. So literally within 1 retry, we were able to, because of read while write, sorry. If we didn't have read while write, that would be a bigger delay because you need the full object to be downloaded, but 50 milliseconds is all you needed to get the headers back. Once headers are back, ATS allows you to hook onto the same object and stream it. So yeah, literally that was the window where we had this leak problem before. Yeah. Any other questions?
Oh, sorry, I just try to get very clear. So you're saying that, okay, if there's a cache open write fail, I go back to have schedule for a later cache open read again.
Correct.
And
yeah.
so after that get passed, I will go back to trying to get the open write lock.
Right, yeah.
And so it would be keep.
No. We'll have to have some mechanism to detect that it already went through that state and not do an
Also,
infinite loop. Yeah.
just one time.
Yeah, obviously. Yeah.
Or how many times it is?
One time, yeah. One time should, I mean, that's what I'm thinking. I haven't actually coded it, but Ivan already has a PR apparently, so we can also, I don't know how he did it.
Right. So one other things I was like when I was playing with this is that we have the transaction timeout, right? Mm-hmm. So the other thing is like one thing I try to tune my stuff is to say I do the open read retry and open write retry together with the timeout, so that if I fail all the retry, I would have already reached the transaction timeout. Mm-hmm. So then I would just be sending the timeout response back to the user for that. So that's one of my way of doing this. Yeah.
Yeah. Transaction timeout. You're talking about active timeout.
Yeah.
Transaction. Yeah, that's usually fairly
inactive
large.
timeout.
Inactive timeout. Yeah, even that is usually fairly large in comparison to this, because this is the whole window is, I think it was less than 1 second for us. Like I said, 50 milliseconds over 5 times or something. So that's like 250 milliseconds at most. And because we had the client-side resiliency to retry as well, we prefer to actually return back an error. Because the other part of this is also that this is live streaming, and after a certain point, that segment isn't useful anymore. So user has already moved on. So even if you waited for 15 seconds or whatever is a transaction active timeout, that's well past the segment duration.
Yeah. So for example, if my like inactive transaction timeout is like 5 seconds,
Yeah.
and then my the open cache open timeout is like 50 milliseconds, then
Yeah.
I'll try it like
100 times.
100 times for that. Is that like too assert or something like that? And like without the statistic of how many retry it
I
is,
see.
it's hard for me to understand like
I see.
am I doing too much or stuff like that. Yeah.
I think that's why we've added this as a model of delay and number as opposed to just wait the whole duration at a shot, because you want to keep checking, because you're literally just waiting for the first byte to come back from origin, just the headers. If you just waited 5 seconds in one window, that's not good enough, because you're literally waiting 5 seconds even when the object is already there in the cache. That's why it was devised in this fashion, where you check frequently so many times. In terms of how much you want to wait, I think, in most use cases, I've not seen this particular window to be larger than a second. Yeah, I think Leif also uses this. I don't know what values they use. OpenRead, retry, what are the values that you use? Is it like fairly large, or is it seconds?
The multipliers and low number.
Number of seconds, really? Okay. Okay. 10 milliseconds. Okay. Wow. Yeah. Yeah, it's a lot of CPU, and also I don't know if you can actually guarantee 10 millisecond scheduling. So yeah, that may be a little overkill. Yeah, we had we tuned quite a bit. Like we went over a few experiments, and then we got to these numbers, 50 milliseconds at 5 or whatever. And even there, our P99 was 1 retry, literally. So it's just 50 milliseconds, and we barely ever had 5 retries. And usually, when it gets to 5 retries, the transaction is aborted. The client just goes away for other reasons. So it's not a successful transaction anyway. So yeah, but that's totally tunable, and the settings allow you to tune however you want it. Yeah, had a question.
So for the stale water validate, like it seems like usually the stale water validate is to shorten the latency for the client. But
Right.
Waiting.
Right.
You might serve nicer. But
Right.
You're still waiting. Like usually the case for this is to like
True.
thing and go immediately.
That's true. Yeah, that's totally valid. That's why it's not exactly stable validate. But given the delay is only 50 milliseconds or 100 milliseconds at most, it's a reasonable trade-off. Because to really do stable validate, the only way we could do is to maintain a duplicate copy of the object, because we are writing to the same place where the object was. The plugin that we had did that, but it had some other problems. It had memory issues and crashes, and there was no support to it as much. I think Kit still uses that plugin. Do you? Okay. 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 Yeah, I think in favor of this, if I remember correctly, we deprecated that plugin, or maybe there were other reasons, I can't remember exactly. But at least from the core point of view, this seems reasonable to do. Yeah.
What I think you used to say in the summits was that the internal version
Yeah.
worked and the open source one didn't work.
Possible, yeah, that's possible.
So if your request comes in and it gets put into this waiting state,
yeah,
that means there's already a refresh in progress, right?
that's
That
true. Yeah,
somebody else has already requested it from the server, so
right.
you're gonna get a response faster than a normal refresh.
That's correct. Yes. Yeah. That's why it's just 50 milliseconds or whatever. As
So you're not
opposed
gonna
to
be waiting very long.
Right.
Yeah.
So that's the trade-off we made, and the net result is that you actually serve fresh copies all the time, as opposed to serving stale copies with no delay. So that's the trade-off, literally. Yeah. That's correct. Yeah. So that is a inherent design in ATS, because there is no distinction between a cache miss versus cache refresh. in ATS. You need to know whether the object you're downloading is cacheable. Until you get the response headers, you can't really tell that. Although maybe in a refresh scenario, we know that, I guess, right? Can we trigger read while write even sooner for refresh scenario? Unless the headers could change. Right. Yeah, he's gone.
This is where the caches come a buster. That's why it's so hard to do this.
Right. Right. Right.
You kind of lose the link once you
That's
go
correct.
forward.
Yeah, that's correct. Yeah, it's an inherent design flaw or limitation or maybe behavior. I don't know how to call it. Yeah, unfortunately, we have to do that. It's both good and bad, I guess. Any other questions?
So what do we need to do now? We just need to land Evan's cache.
Yeah, we'll sync up to see what other changes we could make. Maybe we can get rid of open rate fail action if possible. That's my thinking. It seems like his patch still has that as a signal to do this behavior.
You guys gonna be here tomorrow?
Yeah.
Quick stuff. And we actually powder. The work did work real well. Let's take a look at it.
Yeah.
Sync up the three of us.
Sure.
Cover all the bases.
Yeah.
Yours is a plugin or a core?
Yeah, that'll be great. Cool. Thank you.